Now we have a function f of xy that is defined by xy over x square plus y square, and we are going to indicate that xy is not equal to 0, 0, so that the function is well defined. Now, say we would like the limit of this function at, say, 0, 1. That is not equal to 0, 0. So in this case, I got a polynomial in the numerator, a polynomial in the denominator. So we have 0 over 1, and the limit simply comes out to be 0. Now, let us consider another case. Say we are going to consider the case in which xy goes to 0, 0, because remember this, even though the function is not defined at 0, 0, still we can investigate the function for having a limit at 0, 0. So let me just go to a different board now. Now we want to work with the limit as xy goes to 0, 0. Excuse me. Xy goes to 0, 0 of the function that we just took. Okay, that is, I'm just going to write the expression directly, xy over x square plus y square, and the substitution, it doesn't yield any determined value, so this is indeterminate form. So we have to use some other techniques to make a determination here. So one thing is there, you might remember that for substitution, I have a product of xy here, and here I have x square plus y square. So sometimes in such cases, okay, and in our examples, okay, actually oftentimes, right? But it's not guaranteed to work, but let's just try this. So this is r sine theta, all right. So what happens? X square plus y square becomes what? R square, right? Because of Pythagorean theorem. And in this case, what is going to happen is this, that if we substitute these values, so we get r cosine theta so x can be replaced by r cosine theta, then y can be replaced by r sine theta, right? And then on the bottom, I have r square, okay? Sorry. So we got r square, and then you can see I have r square in the numerator and r square in the denominator. So those two will cancel, right? So what it comes out to be then, the limit as xy goes to 0, 0 of cosine theta, sine theta, and theta, when we are at 0, 0, we can determine that, and the value of theta is going to influence the value of the limit. Okay, so for different values of theta, we will approach different values if we go via this route. For example, say we are looking at this going via route y equals x, right? Then in that case, this will become, if you look at this, if y equals x, this is simply, I have x here, so this becomes how much? Let me just move this left a little. So that is going to become x square over 2x square, and we can assume x to be not equal to 0 before applying the limit, so that will be 1/2. And on the other hand, we can just keep playing with this in different manners. So say we go via negative x. Okay, so this becomes what? Negative x here. Let me erase this because this is kind of a little misleading. Okay, and negative x square will again be positive x square. So this quantity is going to be negative 1/2. Okay, so let's go to Matlab and see how it looks graphically. Here we have the Matlab opened and we are working with live script. So let's call for a live script here. And here it is. So what we have is that we are writing for a function of two symbols, x and y are two variables. So we shall just first tell it that they are symbolic variables, and then as usual, we go ahead and type our expression in. All right. And now, so here is our expression. Now for the graph. So for a graph, what I am going to do is it takes f surf as, sorry, not in this line, the next line, f surf as a command for the graph of a surface. And let's just stick to -1 and 1 because we want to stay near 0. So here we should have a graph of f coming up. So here we have a graph, and now you can see that this graph is I mean, we can already see that at 0, 0 we have a problem, and graph approaches the value 1/2 as we approach, as we proceed via the line x equals y or y equals x, and -1/2 via y equals negative x. Okay, let's take a slightly different expression now, and of course we must indicate that xy is not equal to 0, 0. Okay, so what we have here is that if we go in our earlier style and let's say take x equals r cosine theta and y equals r sine theta as we did before. So x is r cosine theta and y is r sine theta. Okay, then in that case, what will happen? We did this calculation a short while ago in a similar, with a similar example. So we have r square and then cosine square theta, right? Cosine square theta. And then we have r, okay? And simply sine theta, because y is r sine theta, and x squared plus y squared by Pythagorean theorem, that will become r square, right? Now, if we simplify, r square and r square will cancel, and here xy goes to 0, 0. It amounts to the same thing as r goes to 0, right? So we have what we got here, r cosine square theta times sine theta. Okay, so now what we have is that we have this factor going to 0, and whatever the value of this factor is, it is going to be between -1 and +1. So no matter which path we are taking, the two will always multiply to 0. Or another way of looking at this is this, that is, if you look at the absolute value of r square, r cosine square theta sine theta, since this is always less than or equal to 1, we have this quantity less than or equal to 1. And here on the left hand side, what we got, since we have absolute value, that will always be greater than or equal to 0. All right, oh, I should say R actually. This quantity is less than or equal to 1, and 1 times R will be R. So as R goes to 0, this will go to 0. This is already 0. So by squeeze theorem, what is going to happen? That this limit will come out to be 0. Okay, now let's just take this opportunity to verify this limit via just some different or using just some different methods. Okay, so I'll just take a few minutes to illustrate some other approaches to you. So I just decided to take a new live script. So in that, all that I have to do is change this to x square y, right? And now I am just pressing Control Enter on Windows. Okay, and we will see what a graph looks like. So the graph looks like this, right? And we can see no matter which path we use, for instance, if we go to uh, 0 via y equals x, let's just go ahead and plot the line here, okay, or that particular line. So I'm just saying sims t, and you haven't seen that a way you plot a line is this. If say I'm going via the approach y equals x, so if I take x equals t, y will be t, and what z will become t cube over 2t, sorry, t cube over 2t square, that will become t over 2. Okay, so then we have negative 1, 1, and we will, let's make our line width as 3 and keep the color as black, okay? And then if we say Control Enter, see, so we will see that particular curve and it approaches uh, 0 as xy approach 0, 0. Now let's try another approach. Say we go via y equals negative x. So this is negative t, and then there we will have negative t upstairs. Okay. So in that case also we see that it goes to 0 as xy approach 0, 0. And just for entertainment, let's just see one more approach. Okay. So let's just keep these graphs on. Sorry, 1 second. So we are keeping the graphs on. All right. And then I'm just going to make a change here because let's go via parabola. So here y equals x square. So if y equals x square, this will be t square. And what we get here is t square plus t square times t square would be, in the numerator we have t to the power 4, and in the denominator we will have t square to the t square plus t to the power 4. So what will that will come down to? I don't have to make the cancellations right here, but anyways, I decided to. So let's keep this way. Okay, so this is the parametric equation here. Okay, and then we can do this, that we can change the color also. One moment. We can change the color also to, see, I'm just got too many things in my head. So this is red. Okay. So now if we look at this approach, what we shall see is that as we approach, as xy approaches 0, 0 via y equals x square, the functional value goes to 0. But keep one thing in mind, doesn't matter how many different paths you take, that's not really a proof. That's just an inductive, you know, just an inductive calculation for you to be able to conjecture. All right. So now let's take this opportunity, because this function is looks like it's easy to deal with, to just verify this definition that under appropriate assumptions, we have this limit xy that approaches AB, okay, if, or limit of xy approaches AB, where f is defined in an open neighborhood of AB, except for at AB, so that equals L if for each epsilon greater than 0. All right, so here is an epsilon. Okay, let's get a better looking symbol. Okay, all right. We can find, or there exists, I will just use, we can find a delta greater than 0. All right, delta greater than 0 such that, such that whenever we have the distance between x, y, and AB less than delta, so what is the distance between x, y, and AB? That's the square root of x minus a square plus y minus b square, right? Okay, b, and here we have y. So whenever we have this quantity less than delta, okay, what has to happen? We must have then, or let me just write in this second line, that this implies that the distance between fxy and L will be less than epsilon. So, this is what people typically call epsilon delta definition. So we are going to look at that in terms of this example. Okay, so now we shall just illustrate this definition by using the example that we just worked with. And I changed the numerator to 5 times x squared y. I didn't have to, but I just changed it to, bring in a slightly different flavor. So what we want to do, we want to find, the value of this delta for any given epsilon such that if this happens, then this happens, right? So let's see. We have fxy minus L. The absolute value has to be less than epsilon. So I just wrote fxy, L is 0. So that's what this is going to become. And what does this mean? This means that, this will be true if and only if what? I have, excuse me, okay, I have this. So in here, what we can see is this, that other than y, everybody else can be assumed to be, sorry, non-negative, right? Okay, and so here let's just write 5 over here, okay, and put it as 5 times so that I know this is not a mixed fraction. Now this quantity here, you can see that this is going to be less than or equal to 1 always, because the denominator is more than the numerator. Okay, so if this is always less than or equal to 1, then what will happen? This quantity 5y will be greater than this quantity, right? 5 absolute value of y, I mean. So what we get here is that we can drop x squared plus y squared, okay, because that is less than or equal to 1, and we can get this. So what we are trying to do here is this. like, making all these symbolic manipulations and everything, just to obtain a condition in which this comes out as an implication of this distance of xy from 0, 0, okay, to be less than another quantity that we can write as delta, right? So we got that. So what we have now is that we have, this is, these two are equivalent. Now notice this here, that if you look at this absolute value of y, okay, then absolute value of y is what? That is square root of y square, right? And remember what we want to bring in here, this expression where a and b are 0, okay, and we got a square root of y square, and all we need is an x square in, over here. But now we can easily see that this quantity will definitely be what, less than or equal to x square plus y square, because I'm just adding a positive quantity to y square. So what we found was that absolute value of y is less than this quantity, and that's what we needed to work with, right? So we can now write this for this here, that is, replace this by square root of x square plus y square, and that is what we needed, right? So what we see, if 5 times the square root of x square plus y square is less than epsilon, then fxy will be less than epsilon, or we can just abbreviate it all as what, as this, and I'm making this video with nobody interrupting me, because it doesn't go as smoothly in a live class as I'm able to do it here. So what we find eventually is that, since we have, I can't have, let me scroll up a little, okay, so I have this, that, see, I can't have xy as 0, 0, so we will keep 0 less than that. So this less than epsilon over 5, what does that imply? That implies that the function minus 0, the distance between those two, is less than epsilon, right? So who is delta? Delta in this case comes out to be epsilon over 5. So for any given epsilon, we got delta as equal to epsilon over 5. So let's take a numerical illustration of this just to see that how this works, all right? And so when I did such an example in class, I know somebody thought that epsilon equals 0.01 was quite small. So I said, okay, let's take epsilon as 0.01. So what we are going to do is that we are just going to see, excuse me, that if square root of x square plus y square is less than a fifth of epsilon equals 0.01, then this condition will be satisfied. I hope you are still with me, okay? Because here you have a luxury that you don't have in class. That is, you can just, set a stop on me. All right, so this is what we got here. And then we got this, and that's going to be who? 0.002. So what we want to see is, let's see if this happens, that if this quantity is less than 0.002, all right, then what is going to happen is epsilon, sorry, this quantity is going to be less than 0.01. So we are going to just look at it numerically, and then we'll employ Matlab to see if we can see it graphically. So graphically, how we would see it, that if x and y, they are in a disk of, in an open disk of radius, this is small, then this quantity or the functional values will be within 0.01 of 0. Okay, so I'm going to use here like widely used spreadsheet. Oh, I took moving averages in coronavirus data. We see it a lot. I want random number generation. So what I'm going to do is that I am going to take x and y. All right, that's why I'm taking two variables. Okay, and I am going to take them between negative 0.0022 to 0.002, and here notice this, that we are really not taking it in a disk. This is actually a square, which is much bigger than that disk, but let's see what it gives us for those values. Okay, so here we go, and these are just too small, so let me make them bigger, bolder, and slightly bigger. Okay, so there they are. Okay, so these are, these are the pairs of values near 0, 0. Okay, whose and they are within a square. Okay, of I think side would be 0.004. I shall show it to you in a moment. And what we are looking at here is 5 times x square times y, okay, divided by x square plus y square, right? Okay, and I said this, so there we go, and it computes the whole thing for us. And let me just take it to a different cell here, sorry, different column here. Okay, and I shall just paste the values, okay, so that I can sort them. All right. So what we want to, so here we had, those values in a square of square whose 0, 0 is at the center, and it's like little bigger than the circle. But remember, in our calculation, the circle didn't really have to be that small. So I'm not going to say all this verbally that much. Let's just look at it numerically here. So first time, what I'm going to do is that I'm just going to sort it. Okay, so data, and I want to sort it. So when I'm sorting it from A to Z, you can see that the smallest distance is less than 0.01. And if I sort it from largest to smallest, that is less than 0.01 as well. That is what we mean to say is this. That is, if we look at what we have just accomplished. So then notice this. So our values are, within this square, okay? And let me show it to you in a different window. So what we saw was that if we take these bunch of points, which are well within a circular disk of radius, how much? Point, it says here, let me write it boldly, bold, 0.002. So these are our xy's, not all of them, a bunch of them that we selected. Okay, so what we saw was, so we saw that the functional values will be, or if I just apply the function on these, they will be between negative 0.00498 to 0.00495 with 0 in the middle. So this, this range is too, quite narrower as compared to the distance point 0, 1. And for these selected bunch of points, what we see is that is true even for outside of this disk. And if you notice, maybe we did not have to take the disk to be as small as we saw here. A larger disk might work, but there we were just going by estimations and the dominating quantities as they conveniently came. Okay, here is a graph that I made for you in the Matlab, that this is our fxy, the surface. Here we have 0, 0, and the radius is 0.002. And if you look at the images of all these points, they are well within 0.01, from the limit that was supposed to be 0. Okay, so hope this all made sense to you. Words, we have everything inside of this disk mapped onto this region, right, which is well within 0.01. So I think I'm over explaining it now. So let's move on to a different example. Now, if you are still with me, I'm going to take just one more example. That is, we are going to discuss, and for x, y are different from 0, 0, everything should be good here, right? So we are going to look at xy goes to 0, 0 for this function, right? Okay, so in here, say we went with our, just a second, sorry about that. Okay, so say we went through our usual route, that is, say we took x equals r cosine theta, okay, and y equals r sine theta, then what happens is this will be limit as we did before, r goes to 0, right? Okay. And then we have r cosine theta, r sine theta, so we will get r to the power 8 upstairs, right? And then we shall have cosine theta to the power 4 times sine theta to the power 4. Okay, all right, just, I don't know whether I should have done this algebra before or it's okay to do it with you. But anyways, so this is what we have, 8, no, sorry, 4 here. Now, an r square will come out as a consequence of this, and we will have r to the 4 here. And r square combined with this 3 will become r to the 6, right? So when we factor that r square out, that will leave behind a cosine square theta, right? And then here we have r to the power 4 taken out, so that will leave an r square behind, right? And then we will have sine theta to the power 4. Okay, so now what we have is that this changes to, when we do the cancellations, okay, so we got r to the 6, or r to the 8 divided by r to the 6 will simply become how much here, or let me just write it here, r square times all that, right? So now we will be in good shape provided we can size this thing, right? Okay, so let's go ahead and see what it looks like. Let's give r real small value and then look at a graph. Okay, so here we go, and I'm just, so it does not look like, let me first shrink it. Okay, all right, so here it is. Okay, and the upper limit is 0.006. So let's just change the view here. So say we change the view to, let's do that to quite big 1000, but you can see that it's increasing without any bounds. So it doesn't look like that this approach is going to work, right? Now say we did this, let's just try different routes. And remember this, the same limit through different routes does not necessarily mean that it will have the same limit, right? Okay, so one moment. So let's just go ahead and say try the route the way we were doing before, y equals x. Okay, so if we do that, what this will be x to the power 8, right? I'm trying to do some calculations in my head. Hope I don't make any mistakes. Okay, and so this will be, what this will be then, x square, okay, divided by 1 plus x squared to the power 3. Well, this is at least, so this goes to which value? This goes to 0, right? Okay. Now, likewise, say we changed x to negative x, all right? So we are changing x to negative x. And if we do that, I don't think it's going to change anything. Still, it will go to 0, right? Because, this is just an even function. So let's try, say, y equals x squared. Okay, so here we got y equals x squared. And if we do that, what we get is, in case y equals x squared, okay, if, right? So this will imply that this is x to the 12, okay? Then I have x to the 6 on the bottom after the factoring. And here we have x to the 8, so that will leave behind 1 plus x to the, 6 squared, okay? And that is x to the, so this also goes to 0, okay? So, but as I said, it's not enough to say that this guy will go to 0 eventually. So let's look at a graph of the function, and I'm not going to type in the commands. I already did those, okay? So I said that here I have all these, all these commands that I already typed up. And let me say Control Enter, okay? So we have this, and so let's just go ahead and take this graph to a different window. Here is a graph with the pictures. So this is the x-axis, this is the y-axis, and this, black approach here is going to 0. That's corresponding to the line y equals x, and this red one corresponds to y equals negative x. They are going to 0. This parabola that was y equals x squared, that also takes it through 0, 0, right? So it looks like all the paths are crossing 0, 0, but we may notice this, that we have not taken anything that may go along this line or shows us something like this, okay? So just remember this, x squared equals y equals x squared or negative x squared, they look like this. So let's go in this orientation here. That is, how about considering y square equals x. Okay, so just a thought. All right, and such thoughts come, may come to your minds much better than mine. Okay, so now we are going to take the route. Which route did we think of? Y square equals x. Okay, so what would that do for us? So if y square equals x, then this guy would be, so what do we get? Y square is x, so that will be simply x square, right? Okay, this will be simply x square because y square equals x means y to the 4 equals x square, right? Okay, so what we get then is x to the 6 here, and one sec, why am I writing? I left a typo here, just sorry about that. Then copy paste kept on. So if we go ahead and factor x square out, then that will factor out as x to the 6. And now we have a different value, right? Okay, that is, this doesn't go to 0 anymore. Now, what do we see? It approaches 1/2. So the function does not have any limit at 0, 0. So let's go ahead and look at this graphically. We know that it doesn't have any limit, but let's see what's going on graphically. So here I have, but now again, I have already, typed in the commands, and I'm going to bring it in here, provided it just lets me go to the next line. So we'll say, hold on. Okay, now here I got that. Let's see what it shows. Okay, so it's coming up. Okay, so here we have a graph, and we will take it to a different window now. So now we see that, via this route, it definitely does not go to 0. But what is bothering me is this, that it doesn't seem to go to 0.5 either. Remember, we said 1/2. So that means I must have messed something up in the calculation. So we can see this here, that we are concluding that the limit is not equal to 0. But looks like I made a mistake in calculating the outcome. So here what we have is, so these guys will cancel, right? And oh man, this is 2 to the thirds, that will be 1/8, not 1/2, okay? So what do we conclude then is, we conclude that the limit at 0, 0 does not exist, right? So I made that little mistake anyways. Fortunately, we caught it, and it says that it's time for me to quit making video right now. Okay, so we will just write this here. It doesn't exist, and it doesn't mean that all the limits won't exist. Okay, that is, we will see other examples, and we have seen other examples in which limits do exist. Okay, so just post the questions in the discussion area. All right.